Welcome to part 6 of Data Analysis 2. This is the Bootstrap. So we mentioned Introduction to Modern Statistics earlier by Chetinkaya Rundell and Joanna Harden. There are links here to the sections that would help you understand bootstrapping and work through tutorials in greater detail. I'm going to do a quick and dirty version of this. It would behoove you to consider working through these examples in a more systematic way in the text and in the supplemental tutorials on inference and on inferential modeling. You'll find useful examples to work through on these, and my examples are actually modeled off of this kind of approach, but that's a good place to get more information. So the Bootstrap, there was a technique called the jackknife, originally developed by John Tukey, and that was evolved into the Bootstrap, developed by Bradley Ephron. And the Bootstrap is an empirical method that's generated by computer simulation. And at the time it was developed, computer simulation was expensive and difficult, and now it is widespread and easy. And the Bootstrap is actually something you can use in many different settings and circumstances to provide estimates. So why do we want to bootstrap? Well, when we do traditional statistics, we're actually making some assumptions that are usually reasonable, not terribly strong assumptions about the behavior of the data, the distribution that the original data that we're sampling from comes from. But often we have no way to really verify that those assumptions are true. We might want to have an approach that doesn't require those assumptions. The Bootstrap gives us this. So we can take an existing empirical data sample and understand the variability of that sample simply via computational methods without making assumptions about the data. How does this work? We take our original data essentially and we resample it and generate multiple what we call sample replicates to work with and understand, build our statistics off of. So instead of looking to the distribution, the theoretical distribution, we look to the empirical distribution generated by our own resampling. Call it the Bootstrap because we are pulling ourselves up by our bootstraps and creating our own estimates of things like standard error. Now there's a package called Infer in the tidyverse that makes this really easy. Now, if I describe that process to you, you could probably imagine that you could write your own code for this and write some code to run loops and generate samples and things like that. But Infer gives us a very neat and clean way to do this. And we have a 3-part sequence of commands: specify, generate, and calculate. We specify the variable we want to sample. We then generate the number of replications or resamples that we want, and from that we can calculate a statistic. So I'm going to look first at, and I'm going to switch over to our studio view of this. I'm going to first just estimate a point estimate of a specific variable. In our data set, there's a variable that says a woman can work in a job as dangerous, deemed dangerous in the same way as a man. So are women basically restricted from dangerous jobs in this country? and the answer is given as a yes or no, just a very general answer. Now, if we average the yeses and nos across all the countries in the data set, we would get the average proportion of countries meeting these criteria, right? So we have, if the result comes out 0.7 as our average, that would mean that 70% of the countries are places where a woman can have equal access to dangerous jobs. So the syntax here is I'll talk through this command since we haven't really talked about this pipe in the tidyverse world, a common syntax feature, but we haven't talked about it in this session, so bear with me here. If I want to read this command in something approximating natural language, I'm saying create something called point estimate that is generated by or assigned using the assignment operator from gender data final, which is then specified, and we specify the variable woman in a dangerous job, and then calculate the statistic mean, right? So I usually read these in my mind as and then do this, and then do that. Take gender data final, and then pick woman in a dangerous job variable, and then calculate the mean. So if we run that, we will get a verification that something happened, but it won't print out until we type it. We'll type point estimate here, and it'll show us that proportion is 0.455. So in our small sample of 12 countries, one of which was removed because it was missing, we have 11 valid entries. Basically 5 of 11 of those countries are countries where a woman can do this kind of dangerous work. But that's just a point estimate. If we want to understand how variable this information is, that's where we want to turn to the Bootstrap. So the generate command is now added in this second chunk that we're looking at, specifically on line 538, where we ask for 50,000 replications of the type Bootstrap. There are other types, but we're just going to focus on Bootstrap here in this session. And we're going to pass this result into bootdist dangerous, right? So that's the Bootstrap distribution of this dangerous work. And you can see, okay, perform that operation. If we actually take a look at this object, bootdist dangerous, we can see it's 50,000 means, right? So just like we calculated one mean for the original data, we are now resampling that original data to get 50,000 new means. And because we are sampling different alignment of those countries, right? Countries can appear more than once in our resample, but they're still drawing from that original population. We get a variety of proportions. They're actually all based on the 11ths, right? 4 11ths, 5 11ths, 6 11ths, etc. So you see repetition of the actual values because of the limited nature of this data set. And we will now use this to understand what is that variability, right? So this part I'm going to do piece by piece. And I'll move my video out of the way. You can see that our mode is near the actual original sample, 0.455, but there's some variability, right? It goes from very low to higher numbers. Looks like 11 of 11 that we didn't quite get there. And we also have this way to shade the distribution to see where the tails are, and the tails are really already it shows you the data is fairly centered on that original mean. And then we can also produce a confidence interval, and you just using this command get confidence interval, which will show us the confidence interval of our estimate is from 0.16 to 0.75. Okay, and partly because this is a very small sample, even the greater you reach a point, you have to replicate a certain number of times. Maybe 1,000 is enough, or 500 is enough for something like this. 50,000 may be overkill. Like, you reach a point where the extra sampling doesn't really change what happens very much. There's always a little bit of random variation. But our confidence interval is wide, not because of the number of resamples, but because of the small initial population, right? And so we understand we have a small set of observations. We can't rely on that for super precise predictions. If we view that as a sample of all the countries in the world, we're only looking at 12. But now we have a quantifiable estimate of that interval, which we didn't have before. This data, if you go back to the way we originally selected it, we didn't really select it as a random sample. So that's, I want to point out that's a problem here for this sample data. What we really want to look at are cases where we have randomly sampled from the original population, and then we're trying to understand the behavior. So that's a confidence interval via Bootstrap. We might want to try other things like we've already done in this session, like a t-test. What about a t-test without making an assumption about alignment with the t-distribution and things like that? We can simulate a t-test via the Bootstrap. And in fact, the quickest way to do this is there's a built-in function in the toaster package that we loaded way back in the beginning. This is where it comes into play. It's called boot t-test. And in this example, what we do is we're going to not do a paired t-test at first, because this toaster package doesn't work well with pairs. Then we're going to see a different example, but we're going to take the labor force participation of males and females. Instead of asking it to do a paired t-test, we're going to simply subtract one from the other. So, U.S. labor force male participation minus female labor force participation. And based on what we've seen earlier, that's going to pretty much be positive for all these countries. But we're going to compute it as a new variable called labor diff. We can actually take a look at it and verify, is it positive? There's one case right here of negative 3.8. So that is whichever our 10th entry, that's Turkmenistan. Okay, yeah, Turkmenistan, always an unusual one, but in Turkmenistan the female labor participation rate is higher than male labor force participation. Once we've computed this, you understand we've encapsulated the concept of pairing the data into one variable. So now we can test a single sample t-test, one sample t-test on this variable with the same implications, the same result. And all we do is we say the name of the variable and the number of replications. It will give us a result, and we now have a confidence interval between 8.8 and 29, right? So it is still significant, still a high mean difference and a decent confidence interval for the difference in participation. We could also try running this for some different replications, and when we run it for a small number of replications, we'll see that confidence interval starts to wander around a bit. However, it doesn't make an enormous difference, and once we get to larger numbers of replications, I was about to say it's more stable. Is it more stable? It's hard to say exactly. It's just proof that this is a random sample that still converges to similar results. Okay, so now we will use the Bootstrap to estimate the variability of the slope in a regression. This is very similar concept, but I just want to introduce this one because there is a fourth verb or step that we can use with infer called hypothesize, and that comes into this kind of statement. Right, so I'm going to create something called var slope, and here I'm using this modified, I passed over this in the notes, but I talked about the pipe percent greater than percent in tidyverse is also equivalent to this base R vertical bar greater than, right? So in base R we can also use a similar concept that's relatively new that was not originally in base R, but we can use that syntax here. So that's the same thing. That's the passing from one line to another. So we take gender data final and then specify a regression, a relationship with our tilde sign, female labor force participation versus fertility rate. We're going to hypothesize that those two things are independent, meaning that we wouldn't expect to see a positive or negative slope. We'd expect to see zero relationship between those two. So now we're going to generate 500 repetitions. Here the type does change, right? This is no longer Bootstrap but a permutation, and we calculate the statistic is not the mean but the slope of the regression. So basically the coefficient of the regression. And by ungrouping the data set, we can then calculate the mean and the standard error across the entire bootstrapped process. Right. So let's take a look at that result. And I believe I need to print out these. Let's see. Okay, so those are our 500 rows. I feel like this part should have actually printed out our results. There we go. Okay, yeah. Either it sort of swallowed that because it was inside the code block, but this section from 598 to 606 does actually produce the mean of the means and the standard error of all the standard errors, which is negative 0.09 and a standard error of 6.07. So the slope relating these two is a negative one. Higher labor force participation means lower fertility rate, except that the standard error is larger than the size of the estimate itself. So that would imply that they're not strongly related. The main point of that example is more to take a look at the use of the hypothesize option. This is a case where, going deeper into the discussion of the infer package will, illustrate more how those things are done. And our final step will be to look at Python bootstrapping. So once again, I've given you a link because certainly my Python is also coming from copying other examples, right? But here is the discussion of the Bootstrap or the Bootstrap documentation in SciPy. There's a link to more, which is coming, right? A sort of guide of how to do this thing in Python, but I will just give you my quick and dirty example, which simply uses the Bootstrap function from SciPy, right? So we are again using this r dot to bring over the labor diff that we just calculated, the difference between male and female labor force participation. That's the only, I'm keeping it simple and just using that one variable. And then I bootstrap that original data with looking for the mean and the 95% confidence level. And we can, from that, calculate a confidence interval. Right? So you can see the confidence interval from 9.2 to 24.5. This again is bootstrapped, so each time I run it, I wonder if that's a random seed issue, because it seems like it is. Oh yeah, that's because I have set random state equal to 1, so that it's always generating the same results. If I don't do that, every time I run it, it's going to give me a slightly different, but as you can see, kind of consistent low 9s, 24-ish, from low 9s to 24-ish confidence interval, but varying a little bit. Every time I run this, it varies a little bit, which again shows you that it is random, but it's kind of reliable. It's ending up mostly in the same place. And that is bootstrapping a la Python with the SciPy bootstrap function. That's the last code that I'll run here. And in fact, the end of the Data Analysis 2 workshops. So, as always, enjoy R, and you can tack on a little bit of Python with that too. I hope this is useful, and thank you for your attention to this point. Thank you.